Flywheel flippers are one of the most difficult combat robot archetypes to build. One can draw many parallels to the more popular compressed gas flipper, as both use stored energy to launch an opponent high in the air. All flywheel flipper variants aim to somehow quickly couple a spinning flywheel to a flipping arm to transfer the energy to an opponent. While a pneumatic flipper may run out of stored gas after a dozen or so flips, a flywheel type can theoretically flip many times more until the batteries run out. The challenge to this archetype is the mechanical complexity not really seen in any other. I've been iterating on a flywheel flipper since December of 2021, right at the start of my combat robot career. With a 13.6 kilogram class event coming up in mid-January, I endeavoured to compete with my example of this rare and unique robot design. This video will be a brief retelling of the history of flywheel flippers in robot combat, then a breakdown of the iterations I've been through to arrive at my latest concept, which is currently being built. The first flywheel flipper I'm aware of is a 13.6 kilogram sportsman machine called Overthruster, built by Dale Hetherington in 2008. A flywheel is spun up, then geared down to the output in which sits a dog feature. The gearing means the output is spinning slow enough for the dog to extend, be caught by this indentation, and then push on the flipping arm. It appears to work fairly well, with a few other variants of this design being built in the coming years. The 100 kilogram Warrior SKF is next, seeming to have first fought in 2009. A sloped ring acts as a cam, mounted inside a large spinning mass which doubles as armor. A follower is dropped into the path of the cam and pushed by the sloped surface as the ring rotates, firing a flipper. Very elegant and inspired system. Fast forward to 2013 and the 1.36 kilogram Eclipso, then the 2.7 kilogram 3-coil are built by Team Brain Damage. Unfortunately, the links to the build diaries have been mostly lost in the past year or so, but I'm pretty sure they use the same mechanism as the later 13.6 kilogram Jack Reacher. A spinning drum sits in front of a second similar drum that is connected to a winding winch. When the flipper is fired, a Coulson wheel is jammed in between the two drums, transferring energy between the two. A winch winds in the back of the flipping arm.
So we've got the big flipper in the front. As the flywheel drives the coil drum, you can see it turning there. The flipper climbs up and up and up.
Notably built in 2017 by the same bloke is Magneto. Using parts from a car air conditioning clutch, the electromagnet sits snugly inside of a flywheel. When activated, the electromagnet pulls the clutch disc and flywheel together, transferring torque. Said clutch disc is connected to a shaft with a rope winch which pulls in the back of a 4-bar flipper. This machine proved to be, in my opinion, the most effective flywheel flipper until rather recently. It was a large inspiration for my later designs, and the short video the builder made on the design was a huge help. The build diary seemed to have been lost apart from what is on the Wayback Machine, but thankfully I downloaded the photo album before the link went down. I've uploaded it again with a link in the description. The year after came a 1.36 kilogram robot called Roll Cake, built by Charles Graham. It featured yet another unique mechanism, the flywheel driving a planetary gear set that featured a freewheeling ring gear. When the flipper was to fire, a servo would lock the ring gear and allow the transmission of torque. This mechanism both integrated a reduction and reduced the flywheel speed to a manageable level for the dog to engage. Stepping up to 2021, we have the most popular flywheel flipper in the form of heavyweight battlebots contestant Blip, built by Seems Reasonable Robotics. The most powerful and effective flywheel flipper to date, this machine appears to be an improved remix of Magneto's design. A flywheel is spun up and engaged by electromagnets that actuate a cone clutch into the flywheel. After engaging, a rope is twisted, pulling in the flipper mechanism as it actuates. Instead of a 4-bar, Blip uses a rack and pinion to turn the retracting motion into an outward push. Finally, we have another 110 kilogram robot in Warthog. Inside this robot is a large drum that can be spun up to speed. To flip, a set of brakes engage to stop the drum spinning relative to the robot. This slowing effect has an equal reaction to the robot's frame. causing the entire machine to flip backwards. Definitely an inspired design. Each of these machines are trying to solve the same engineering problem, but go about it in incredibly unique and varied ways. Compared to a simple spinner, each and every one of these robots are far more complex and need to dedicate a lot of weight to the flipper mechanism, which is not available for armor. Each mechanism has its polarizing advantages and disadvantages. Overall, flywheel flippers are one of the best examples of what makes combat robots great, an engineering challenge with no perfect solution. Learnings from these machines will inform how I go about my own. Around the end of 2021 was my first shot at a flywheel flipper. Initial prototypes were just a copy of the old 3-coil system, but I soon landed on a unique design of my own, seen here. Called Loft, it was a 150-gram robot featuring a vertically mounted flywheel, rubber friction clutch, and a rope which pulled in the flipper arm. This motor would pull the gear towards the spinning flywheel, engaging the rubber pad to its side and transferring torque. At this time I hadn't really thought about the design and just threw things together, so it had a lot of problems. The rubber pad didn't transfer a lot of power, which limited how hard it could launch another robot. The winch would wind up and tighten, which required strong elastic bands to unwind, but these elastics further removed a lot of power from the flipper. To add to all this, the system was inconsistent and unreliable, but definitely a feat that I learned a lot from, and at the end of the day, it did work. It came with me to my first robot event in Melbourne, where the flipper promptly stopped working and it wedged its way to the semi-finals. A while later, we arrived at my first attempt at a featherweight flywheel flipper. It is very similar to the 150-gram attempt, though with an even simpler flipper mechanism. A flywheel is spun up by this motor via a belt. The clutch pulled into the disc flywheel by a car AC electromagnet, which winds up a rope. That action pulls in the back of the flipper arm to fire the weapon. Positives of this design are the simplicity, low weight, light flipper arm, and sneaky 2-to-1 reduction from a gun tackle on the flipper arm. Less positive is that it probably wouldn't have worked well at all. Despite getting halfway to a finished product, I decided to stop and wait for a better design. It would have been my first featherweight, and I now identify many poor structural decisions and major flaws in the functionality of the flipper mechanism. Firstly, the variable mechanical advantage is backwards, starting at the lowest and ending at the highest, which will make more sense later. Next, the flipper pulley is so far to the left that it probably would have just twisted the fragile arm badly with the uneven forces. Finally, there simply wasn't enough mechanical advantage between the flywheel and flipper for an efficient launch. It was a valuable design lesson regardless, and set the general structure for designs going forward. More generally, the parts from this robot would inform my first competing featherweight called Derive. A centrally mounted vertical flywheel with a slender arm protecting the mechanism rides on a square 4-wheel drive base. The flywheel location was a major point of contention, as it's rather annoying to work with. Magneto offset its flywheel to the side to allow for more space for the winch mechanism itself, but this led to it having severe turning trouble, where it would be stable one way but flip itself over on the other. I'd argue the gyro placement is the greatest flaw in the blip flipper system as well, being longitudinally set with an upward tilt. With the flywheel spun up, it appeared the machine couldn't turn without lifting the front wheels off the ground, and had to wait for a spin up after pinning an opponent. For the best driving performance, this robot will have the flywheel sit vertically in the middle of the robot. Before detailing further iterations, it's worth specifying my criterion for a good flywheel flipper. First, the clutch must engage and disengage quickly and reliably to maximize work and prevent self-destruction. Secondly, the flywheel needs to store ample energy to send an opponent high into the air. Thirdly, the system must minimize gyroscopic effects, and any existent effects need to be predictable while impeding driving as little as possible. Fourthly, the system must have a variable mechanical advantage to optimize the flipping action. This needs to include a no-load state at the start to allow the clutch to spin up unimpeded. Finally, the flipper arm needs to be as light as possible, as its inertia has a large impact on the flipping performance. A year after the ant weight, it was time to give it another crack. Considering the variable mechanical advantage, I didn't actually know what the profile should look like. The latest and greatest idea was to use a cam to push a follower in a design more akin to a usual gas flipper. The cam would have a perfectly circular profile to start with, keeping the flipper unloaded while the clutch bites, and then slowly ramp up the slope to decrease the mechanical advantage. The cam will be geared down from the flywheel, but feature the usual air conditioning clutch. As for the drivetrain, I was interested in using low voltage in-runner motors to replace the high voltage outrunner motors of the previous machine. These would be coupled to epicycloidal gearboxes machined directly into the frame rails for an extremely compact drive setup. Shock-mounted armour worked well on Derive and is seen here. As for the model itself, this was the first robot I ever modelled parametrically. All robots up until now were done directly modelled into one or two files. I blame Fusion 360 for enabling such heretical activities in the first place. The system here met most of my design criteria with a mechanically sound mechanism on paper. Flipper arms were light, the cam allows for excellent tunability, and the mechanism can't self-destruct as the follower will pop out of the cam at the end of travel. Unfortunately, there were a few flaws here too that warrant another complete redesign. While the flipper arm itself was very light, the rotational inertia of 2.5 kilograms of gears will inhibit the flipping action heavily. All those gears only earn a 9-to-1 reduction, which in hindsight wouldn't have been enough. Along with a few structural issues, version 2 is scrapped to have another go at the problem. Version 3 is the one I'm currently going through the process of building. Its mechanism is the best I've come up with, based on something known as a windlass. These use two drums of slightly different diameters to get a large mechanical advantage. As one drum feeds rope out, the other feeds in. Therefore, the load is moved by the difference between rope in and rope out. It will be impractical to have a regular single drum winch with say 2mm diameter, but quite doable to have a pair of larger drums where the difference in diameter is very small. A truly ingenious little machine. My variants went through a few iterations. After splitting the drum in two, the first idea was to have the rope moved sideways up a cone, as it's wrapped in slowly to increase the mechanical advantage. The motion will be transmitted to flipper by rack and pinion. I ruled this design out, as it would be hard to force the rope up an incline under load, even with a groove cut in the drum. The force would also be applied at the extreme sides of the flipper arm at times, which is not ideal. Next attempt had two identically sized drums, but geared ever so slightly different to get the differential windlass action. Variable mechanical advantage came from a non-circular rack and pinion, which you can see roughly modelled here. I decided against it though, as the forces on the rack became more difficult to control near the end of travel, angling more and more downwards rather than parallel to travel. The third sub-concept returned to a regular rack and pinion and differently geared winches, but relies on the top drum's rope wrapping onto itself and increasing the apparent diameter to get a variable ratio. This is the design I'll develop. One point of contention was whether or not to use a rack and pinion to take the pulley motion of the winches and transfer it to the flipper. I spent a good while trying to make a parallel motion watt linkage work, as it had the potential to be lighter, but I decided to stick with the simplicity of the rack and pinion. One really needs the winch tackle to travel in a straight line, which is why the arc-following, simple rear lever of version 1 was ditched. Several parts for this robot were manufactured and provided to me by PCBWay, who are sponsoring this project. They machined the flywheel, clutch plate and axle from 4340 steel, 3D printed some tool steel gears for the drivetrain, and laser cut these mild steel plates which form the flipper weldment, which has almost immediately got covered by fingerprints. The clutch disc fits well onto the hexagonal section of axle, and the flywheel itself is generally immaculate. From the first impressions they appear well fit for purpose, and I'm keen to finish the robot and see what they can do. As the parts are now parametrically modelled, I can easily show how some of the interesting ones are put together. The flipper pinion starts out life as a fully generated spur gear that is cut down and the rest of the features added, including pocketing and finishing fillets. In a similar manner, a long rack is generated and then cut down for the mating component. Complex parts like the large structural uprights are not knocked up on the first try. I had to go back in numerous times to adjust the placement or add holes. This timeline scrub only shows how the computer generates each part on rebuild based on the commands it has queued up for the rebuild process. For complex structural parts that are approximately mirrored across the center of the robot, such as these upright pieces that form the structure of the flipper mechanism, first a base model is created with all the common features. This is copied into 2 new files and mirrored in one to flip it as appropriate. Then the side-specific features are added, such as the mounting for the flywheel motor that should only exist on the right-hand model. This means one doesn't have to do the same work twice, and any changes are reflected in both models seamlessly as they are still derived from that original component. The flywheel mechanism is pretty much as conceptualized. An in-runner motor spools the flywheel, which is engaged by the air conditioner clutch when the time comes. It passes the torque to the first smallest gear, and then onto an idler which powers both winch drums. The top is geared slightly faster than the bottom for the differential action. As the rope wraps on the top roller, it stacks on itself to give a variable mechanical advantage. The rope pulls in on the rear-mounted bar, sliding the rack that turns the pinion and fires the flipping arm. At the end of travel, a pair of redundant Hall effect sensors cause the electromagnet to disconnect and allow the mechanism to reset on these green elastics. I'll cover more on the drivetrain another time, but for now it's a bevel gearbox that drives belts to 2 sets of 2 wheels, based on the system seen in Reality and Equinox. An earlier version of the robot had a heavier flipper arm, enormous in-runner motors on the drivetrain with chain instead of belts, steel framing, and generally just heavier all around. Turns out the flywheel mechanism is very heavy, with the first completed assembly weighing 8.5 kilograms of the 13.5 kilograms I have available. Massive weight reduction followed. Inclusive in this was the selection of magnesium alloy shafts basically everywhere. Magnesium AZ31B is allegedly close to aluminium 6061 in strength, but only 2/3 of the mass. It's also cheap on AliExpress, assuming what arrived matches the description. According to my estimates, that weight reduction was very much appreciated, but time will tell how it works out. I always liked the tanky look of the first version, so it was mimicked here. I finally have confidence in this version of the design, so I've already done most of the machining to bring it to fruition. Compared to my other robots, there are way more parts to make, so I'm already quite behind schedule I wanted to stick to. Next video should include all that machining, detail on the drivetraining, and a functional robot. Until next time.